Good evening, everyone. As a master, it is my pleasure to introduce tonight's inaugural lecture entitled Delving into the Foundations of Future Technologies, One Atom at a Time, which will be delivered by Professor Peter Wahl of the School of Physics and Astronomy. I will introduce Professor Wahl properly in just a moment, but let me say something first about our program this evening. After my remarks, I will invite Peter to deliver his lecture. This will then be followed by a vote of thanks from the Assistant Vice Principal Dean of Science, Professor Gareth Miles, which will close the formal part of the evening. We will then walk over to Lower College Hall, just next door, for a drinks reception to which you're all warmly invited. These inaugural lectures are one of the highlights of our academic life here at St Andrews and play an important role in allowing as wide an audience as possible to hear about the innovative research generated by our world-leading professors. And world-leading is an excellent way to describe the work of our speaker tonight, Professor Peter Wahl. Peter's passion for his research specialization began at an early age. When at secondary school, he was tasked with undertaking an internship to learn about different professions. Peter's idea of what he wanted to do at the time was to become a diplomat in the Foreign Service, because he liked the idea of seeing many different places and having parties all the time. He does note that he's not quite so much the party animal now. However, what Peter ended up doing was an internship at the National Institute for Standardization in Braunschweig, where he was working with a scientist who built a scanning tunnel microscope. He enjoyed this so much that this has now become Peter's research specialization. How did we get here? Well, Peter graduated with a diploma in physics in 2001 after studying at the universities of Bonn and Lausanne, before going on to pursue a PhD degree in physics at the Max Planck Institute of Solid-State Research in Stuttgart, from which he graduated in 2005. This, however, was not quite what Peter had intended to do for his PhD. He originally applied for a PhD in Lausanne, which would have involved building a complex instrument which would enable completely new physics. However, that project unfortunately fell through. This led him to then apply and being interviewed for a PhD position in Stuttgart to build a different machine, also involving new physics, and there's clearly a theme here, which he was successful in being offered. However, somehow when he arrived, the position had been filled by somebody else, and Peter was given a different project, which he admits that at the time he didn't actually want to do. It turned out to be a lucky outcome for Peter, as rather than building a setup, he joined to work one which was operating and where he could directly start with experiments. As sometimes happens, this coincidence and change went on to shape Peter's career. After stays abroad in Aarhus in Denmark and in the US at Cornell University with a prestigious Theodor Lehnen Fellowship, he returned to Germany, where he led an independent research group at the Max Planck Institute for Solid-State Research from 2008, developing advanced low-temperature microscopes to study quantum materials. In 2012, he joined us here at the University of St Andrews, appointed as a reader in experimental condensed matter physics. He oversaw design and construction of unique ultra-low vibration laboratories for the atomic scale imaging and spectroscopy of advanced materials, and Peter is a co-founder and co-director for the Center for Designer Quantum Materials. In 2018, Peter was promoted to professor in the School of Physics and Astronomy, an achievement we are, of course, here tonight to celebrate. His research aims to identify new materials for future information technologies by using atomic scale imaging and spectroscopy to understand their properties and enable controlling them. Peter has over 70 publications across a variety of journals, and his group have developed and now operates a suite of bespoke instrumentation that is unique in the UK and provides unprecedented insights into the electronic states in these materials. In addition to leading his research group, Peter has taken on the role of Director of Research in the School of Physics and Astronomy and led the school's submission for the Research Excellence Framework in 2021, where the school achieved a fantastic 8th rank in the UK. Just in the last couple of months, Peter has attained a position as a research professor at the University of Bonn as part of our university's strategic partnership with Bonn, further strengthening the world-leading research which forms a fundamental part of our current strategy. I'm going to wrap up this introduction, as I think it is more than clear that Peter is a true example of what it means to be world-leading here at St Andrews. It is fantastic to be here tonight with you all to celebrate Peter's achievements and contributions to our university. So please join me in welcoming Professor Peter Wahl and invite him to deliver his inaugural lecture, delving into the foundations of future technologies, one atom at a time. Peter.
Good. Thank you for the kind introduction, and thanks to all of you for coming to the lecture today. So the presentation or the lecture will be split a bit into two parts. In the first part, I want to motivate a bit why we are doing the sort of research we are doing, and then in the second part, I will show you some key results from our research and explain a bit how we study materials. Before I start, I want to thank all the people who actually do the hard work, because I'm literally just doing the talking. So this is the current group, and these are all the people who have contributed to the results which I'm going to show as part of the lecture. And I also want to mention the collaborations we have, in particular here in St Andrews, the co-founder and co-director of the Center for Design of Quantum Materials, Phil King, and Andreas Rost, with whom I've also collaborated a lot here in St Andrews. And preparing this lecture, I thought I also want to acknowledge all the people who've contributed to building up the instruments over time. So the group is now since 10 years in St Andrews. So I wrote to them and said, well, if you want to be included, send me a photo. And it was actually a great preparation to basically receive all these photos. So all these people have contributed to build up these instruments over 10 years. And even if their results don't feature specifically in this lecture, for some of them, they've kind of contributed to the construction of the equipment. Okay, so let me start by motivating why we are doing condensed matter physics in the first place. And this is a photo of Professor John Allen, who was here professor of physics in St Andrews. In fact, he only just about overlapped with me. I think he was already an emeritus professor when I arrived here, so I bumped a few times into him in the department. And he basically achieved something which I think is almost the dream of every physicist. So at some point, he invented the light-emitting diode in 1961. So he was one of the first people to be able to build a diode which would emit light in the visible range, red light. And we all know that's something we now have in everyday life. We have it in all our houses. It's what now illuminates our living rooms. And it tells us two things. Well, one thing is it takes an incredibly long amount of time from a discovery to actually making it into practical applications. But also, if we understand how we can, for example, tailor electronic states here in semiconductors, we can actually use that control to make new devices which are more energy efficient and which we can use to then, decades down the line, change our lives. So in the case of the light-emitting diodes, so this is a graph here which shows the cost of these light-emitting diodes over time per light intensity, as well as what the light intensity of an individual light-emitting diode was. And you can see in the 1970s, they were very expensive. The blue line here is the cost, and they were relatively dark, so not particularly useful. But then over time, they become more and more intense, and the cost goes down exponentially. This is an exponential scale, so the cost per light intensity goes down by a factor of 10,000. So that nowadays we can basically have them everywhere in our house. And by comparison to a normal light bulb, they are 5 times more efficient. They are about 5 times more efficient. So that's a key example of how we can achieve sustainability by more efficient technology, right? In this specific case, by changing your light bulb, where 90% of the energy which it takes up is converted to heat. So effectively, you can actually better heat your living room with a light bulb than light it up. With an LED, you basically convert something like 90% of the electric energy into light. Okay, and so what's the modern light bulb? What's nowadays light bulb? Nowadays light bulb, as you may all know, is if you have a small room and, for example, you have a teenager who's gaming, who's playing computer games in the room, you don't need to heat the room. That's maybe partially the teenager, but it's also to a larger part the computer. So computers take up a lot of energy, and that energy is practically all converted into heat. And so this graph here shows the energy consumption just of Google over time for their data centers. So every email you send, every Google search you do costs a bit of energy. In fact, you can estimate, and sending an email is on the order of a gram CO2 equivalent in terms of energy usage. If it's a short email, it's less. If it's a long email with an attachment or with an image, then it's a bit more. So if you write something like 30, 40 emails and you have a car which doesn't use up much energy, then you can actually drive your car for a kilometer for the number of emails you write in a day, which is quite surprising because you move actually about a ton by a kilometer, whereas if you have written 40 emails, you haven't done any work in the mechanical sense, right? You haven't moved anything. And I think some people will write many more than 40 emails a day. Okay, and so what you see here is that this energy consumption is increasing by 20% a year of Google. And since the pandemic, we all know what happens if we have an exponential increase, right? That's not going to go on forever. It's going to hit a wall at some point. And so basically, there is a problem here. So there is a need for more energy efficient technology. There's a need for new technologies which basically make more efficient use of the energy than what we currently have. And just to compare, the energy consumption of Scotland actually goes slightly down over time. So it hasn't gone up. It has become greener, but it hasn't gone up. And you can estimate in a few years' time, Google will actually have overtaken Scotland in its energy consumption. Okay, and this energy consumption of data centers is so bad that, for example, 1 year ago, there was a report that in London they couldn't build new housing developments because all the electrical energy was going to be taken up by data centers. So they had to build new conduits for the electricity to be able to build new housing developments. And now you might think, okay, with email and Google, we are already done with, in terms of what we expect from computers, the energy consumption isn't going to go up. But then, as we all know, 1 year ago came ChatGPT, and actually those artificial intelligence, these AI systems take up a lot of energy. So an AI prompt is another factor of 10 more than a Google search in terms of energy consumption. So as DOR, one is sometimes pressed for time, needs to write strategic documents. So here's a request to write a strategic document for our school. I haven't used that actually. And it's actually surprising how well it reads. A few years down the line, maybe they will become useful. Okay, and somewhat connected is the question, do our computers actually still get faster? And so when I got my first computer in 1987, it had 8 megahertz. That was the clock speed. And when you went to school and you talked to your peers, the clock speed of your computer was the thing you talked about. So if a friend got a new computer, it would have 16 megahertz or 32 megahertz. But that actually hasn't kept increasing. So if you look at how the clock speed of computers increases over time, it went up until 2003, and then it stalled. And it's for the same reason that basically as you drive up the frequency, it generates more and more heat. And at some point, the heat becomes so much that you can't get the heat away anymore. And so it becomes inefficient to actually drive them with a higher clock speed. If you have teenage children, they can tell you can overclock the computer and then see until it breaks at some point. But that's obviously not meant how one's meant to operate them. So really what we need is, if you like, basis for new technologies. And the international semiconductor industry has also recognized that. So already in 2015, they wrote in the International Technology Roadmap of the semiconductor industry that one needs new technologies which don't just move charges around as we do in conventional technology, but try to use so-called collective phenomena, where electrons move, for example, collaboratively around, where you use the spin of the electrons, or ideally maybe a quantum computer. So what do we mean by correlations of electrons? So let me try to visualize that. Okay, and some of these actually are not just correlative movement of electrons, but also that we control the phase of the material rather than just moving charge around. So controlling the phase of some material, that's a bit like what you do when you put salt on the street in the winter, right? If we are here, this is the phase diagram of water. So here's the temperature, here's the salt concentration. Normally water is at 0% salt. We are in winter at about 0 degrees Celsius. And then when it freezes, what you do is you add some salt to the water. So you go in this phase diagram to the right. And so where normally it would freeze, you go to the liquid phase. That's phase control. And now obviously in a processor or in a memory device, you don't want to sprinkle some atoms to kind of change the phase of your material. But if you can induce a similar phase change in a material, for example, with an electric gate or with a magnetic field by some other means, then you might be able to switch very fast actually without having to move around a lot of electrons. And to visualize these correlated electron effects, here's a piece of music where in the beginning we've removed the correlations. That's here, this noise, where it just sounds like uncorrelated noise. It just sounds like noise. And then we recover these correlations here, and then you can actually hear the music. So basically, when you have correlations, you get formations of patterns, and you get interesting phenomena happening, which is what we'd like to study in our microscopes. Another example of a correlated phase comes from another professor who also is called John Allen, but it's a different person. And so he was also a professor in natural philosophy in St. Andrews, and he discovered superfluid helium, which is a correlated phase of matter. So helium, if you cool it down to very low temperatures, minus 269 degrees Celsius, it becomes liquid. Normally it's a gas, then it becomes a liquid, just like water. But if you cool it further down, it suddenly becomes a liquid which flows without any resistance. So it can basically move around without losing any energy. And one of the interesting phenomena, so he was a co-discoverer of that superfluidity, and so one of the interesting phenomena you can get from that is this so-called fountain effect. So this is a movie made by John Allen, so he made these movies and was actually quite famous for them. And because of him, we have a long history in low temperature physics, and we have a helium liquefier, which is very useful for our research because that allows us to keep our microscopes cold. Okay, and similar to the water-salt phase diagram, what we try to study is the phase diagrams of materials. So what's different compared to the water-salt phase diagram I've shown you is if you have water and it freezes, then it's really the structure of the water molecules changing. In the liquid, they all move around very fast, and then when it becomes solid, they lock into place. Here, the atoms are always in the same place, but what moves around are the electrons, and then the electrons do interesting things. They, for example, lock into place, form an insulator in some cases. They become a superconductor in some cases, like the superfluid helium, or they order into a magnetically ordered phase. And ultimately, what we want to understand is why these materials have these complicated phase diagrams. So in all these cases, you have here on the vertical axis the temperature, and then on the horizontal axis some control parameter. Here, it's just some arbitrary control parameter. Here, this X here is actually sprinkling some atoms in it, just like the salt in the water. And here the scale is magnetic field, and we'll come back to that specific example. Okay, so how do we study these materials? Explorers need ships. Our ships are our scanning time microscopes. This is the Discovery, which you can see today still in Dundee. And these are the explorers which went to the South Pole with Scott. They don't look very happy here because they arrived there and they saw that a couple of weeks earlier Amundsen was there. So there was already a flag, which must have been a huge disappointment. Normally we try to go where no one has gone before. It doesn't always work out. These are our explorers here. They notably look a bit happier. Okay, so these are our microscopes, and I'll briefly describe what a scanning tunneling microscope actually is. We've heard that a few times now. And this is the lab here, which I'll also briefly mention because it's actually a very special and unique lab. Okay, what is a scanning tunneling microscope? So in a scanning tunneling microscope, we bring a metallic tip very close to a metallic sample. Very close means within about 2 radii of an atom. So something like 4 angstrom for the experts. It's 10 to the minus 10 meters. It's really a tiny distance, but it doesn't touch. So classically, you would say, if I have a gap between 2 wires, right, an electrician would tell you if there's a gap, then there's no current. But quantum mechanically, if they are very close together, then the electrons can actually hop from one side to the other. And so if we apply a voltage, we get a small current. But we have to be very close. We have to be those 2 atomic diameters or 2 atomic radii with the tip from the sample of the material. And right, and just to compare that, to give you an idea of what scale that is, if we would scale up the tip of our microscope to the size of Burj Khalifa, which is the tallest building in the world, or was the tallest building in the world at some point, and then we would put the sample on, right, imagine you climb up on the tip and you hold the sample there. You would have to bring the sample within the diameter of a hair of the tip, right? So imagine you cling to the antenna up there and you try to hold something within the radius of a hair, but without touching, right? So even if it's windy or something, you have to always keep that distance, otherwise your sample is destroyed. That gives you a bit an idea of the challenge we face when we try to stabilize these tips in front of the surface. If it works, oh, this is a bit dark, but here's the tip, this is the metal surface. If it works, we can basically raster scan this tip across the surface, and then we can record the current, and then we get an image of the surface. This here is the surface of a gold crystal. There are a few atoms on the surface. These are individual atoms, and the lateral size of this image here is about 20 radii of an atom, so 50 nanometers. So it's really small. It's much smaller than what you would be able to see with a light microscope. Now, these images are nice to look at, but it's actually not the thing we are after. What we really want to do is we want to study the electronic states in the material. And to do that, we have to stabilize the tip at a specific position and then record the current as a function of voltage. So this axis here is the voltage between the tip and the sample. And here it's the differential of the current because that's nicer to look at, but in principle it's the current. And in this case here you can see how the current, how this differential increases, then drops to 0, and then increases again. So we would say there is a gap in the material. In this specific case, it's actually a superconductor. And then we record such a spectrum at each point in a relatively large size, well, for us, relatively large size of the sample. So we get a 3-dimensional data set of the current as a function of voltage and as a function of position. And from that, we can try and understand how the electrons behave in the material. And these are very slow measurements. So such a measurement can easily take about 100 hours, so 4 to 5 days. And within those 4 to 5 days, one must not bump the tip into the surface of the material. Otherwise, the tip is going to be destroyed or the surface of the material is going to be destroyed. So it needs a very quiet environment. And so I was very fortunate then that when I arrived here with a previous incarnation of the master, I was a doctor at the time, we planned these ultra-low vibration labs. Actually took about a year to plan it because we tried out different sites. And in the end, most of them turned out to be not suitable, not because of the vibrations, but because you need to be able to build in the place. And in the end, we decided that the staff car park of the physics building was the best place to put it, which made myself very popular, I think. So this is the blueprint of the building, and this here is the building as it stands nowadays next to the physics building. And one interesting point was when they were planning the building at the time, RAF Lucas was still operational. And we are really worried about the noise from the fighter jets, that they would basically cause issues for our scanning tunneling microscopes. So the engineering office, they did measurements in the courtyard of the physics building of the noise there. So that's these curves here. This here is the frequency of the noise, so the height of the tone, if you like. And this is the intensity. And then the head of estates at the time, John McGuire, or someone from estates phoned up the RAF Lucas and asked them to fly a few jets over the physics building so that they could measure how bad the impact of the vibrations is. I tried desperately to find a photo of that, right? Nowadays, you would have a smartphone camera and you would take a photo. But then in the old report, actually, so it said they had 4 RAF jets fly over the physics building, and the jets were not actually visible because apparently they flew over the cloud cover, so no surprise that I didn't find a photo of it. But they were actually quite happy with what they saw. So this is the noise with the jets, and you see how in this part here, between 100 and say 600 hertz, it's actually quite strongly increased, right? It goes above 80, so up to here on the left graph. But what they were particularly concerned about is down here, this part. And there's actually hardly any increase. And so they were quite happy that they could deal with that and that these ultra-low vibration laboratories will be just fine, even if a jet is flying over it. So this is how the building looks like. And it's a very special design. So we have inner labs, which kind of sit on the bedrock of St. Andrews, and then an outer concrete hull around it. And that outer concrete hull, which is the one you see here, sits actually on sand. So that even if there's wind on the building and it shakes the outer hull, it will not affect the inner rooms. And so even if there's a bit more wind, which occasionally happens, we are not affected by that. Okay, and this is how the instruments look like. So this is one of them. So we built four of these microscopes, and the 5th one is currently under development. And so we buy typically the cryostats. This is a cryostat, it's a thermos flask for helium, basically. And then these are our microscope heads here. They are made out of sapphire, out of single crystalline sapphire, because that's very stiff and stable. So that's very good for these measurements. And one of these is in a dilution fridge. It can cool the samples down to a temperature of below 100 millikelvin. So that's below 273.05 degrees Celsius. So it's just about 0.1 degree, less than 0.1 degree above absolute zero, above the lowest you can achieve in the universe. And so I think up to now it's probably still true that it's the coldest STM in the UK. And why do we need these low temperatures? It gives us high energy resolution, plus some of the quantum effects we want to study. If you go up in temperature, they effectively get scrambled by the temperature. So then the temperature scale dominates. So you want to freeze that out to really study the sample in a pristine state where temperature doesn't play a role. Okay, how do we get the surfaces of these samples? I told you we bring a tip very close to a surface. We need to somehow prepare the surface. It's a very archaic method by which we normally prepare these surfaces. So here is a sample. We glue a rod on top. That's this rod here. The sample you can hardly see because it's this very small thing here. And then we just knock the rod off. And then we hope that it takes away some part of the sample. And if we are lucky, that gives us an atomically flat surface. It doesn't always work, but it works sometimes. Okay, so how do these images look like? So this is the kind of image which then lets our hearts beat a bit faster. When we see these nice atomic resolution images, that's kind of great to be able to see these atoms and to see them so sharp. They are not always immediately so sharp, but with a bit of work, that's the kind of images one gets. So here, this image here, this is an image of the crystal structure. Each of these white points here is one atom in the material. You see them on the crystal lattice. This is a square lattice here, which is why they are here on these square-shaped positions. And now you also notice that there is something different here in the center. There's one atom missing in the material, one atom different. There's a defect. We don't exactly know what the defect is, but it's just one single atom which is different. And now what's curious is that that single atom being different, it doesn't just mean that one of these points suddenly is slightly different, but actually it forms an extended pattern around it, right? You can see how there's these kind of oscillations around it. And that's what we are ultimately interested in. That's how the electrons in the material feel the presence of the defect, and that's how we can learn something about the properties of the electrons in the material. And just to show you a few other examples, this is a different material here where, again, there's just one single point defect, one atom different in the center of the material. Here we have a hexagonal lattice, so it's a somewhat different crystal structure. And finally here, a third example, again, a square lattice, again, a few point defects where you can see extended patterns around them. Now, this third one here, I show in particular because it's an interesting example of how you can make these samples. So these two here are samples which have been grown by collaborators. So we collaborate with people around the world who make these samples and then send them to us, and typically they are experts in growing them, so we would in no way be able to do that. But in this case here, so we went and a decade ago, maybe 5 years ago, for the summer holidays to the highlands, and the children played next to a former silver mine in the highlands, and so they collected some pieces of galena, which is the ore which you have to mine in order to get silver. So it's lead sulfide. It has the same crystal structure as salt, and then actually one can cleave it to make nice surfaces. So this is a piece of galena mineral, where so some of these defects will be silver atoms which are embedded in the material. So it tells you that even if you go, for example, on the beach in St. Andrews and you find a mineral, you might be lucky and find something where you could prepare such a nice surface which gives atomic resolution. Okay, and yeah, these patterns which we see, they are a bit like the ripples in water if you throw a stone in the water, if you perturb the water. So here we like to see that these defects perturb the Fermi sea of the material, the electron sea in the material. Okay, now how do we analyze the standing wave patterns? So what we typically do is what we call a Fourier analysis. So I want to spend a few minutes on explaining what a Fourier analysis is. And I'll again use an example from music. So this is the same music piece you heard in the beginning, played on a slightly detuned piano. And so this is here the trace which shows you the variations of the sound pressure level with time, right? This is the time axis, and this is how the sound pressure level varies. So music, in a way, is just that, right? So you plot it as a time series. Now, if you would give that to a musician and tell them, well, play that to me, they would just laugh at you, right? There's nothing they can play here. So we have found a different way of recording music, which is by a score. And what that score shows you is, well, so here you see the first three chords, right? There's the first chord, the second, and the third. So it's these three here. But then if I only look at the first chord in the musical notation, these are the different tones which you have to hit on the piano in order to create that chord. And that's effectively what we would call the Fourier spectrum. That's the different frequencies which contribute to the chord. So this is the time series of that chord. This is the frequency spectrum, more or less, of that chord. It's an approximation of it because you also have overtones which come in addition. But if you play an instrument, you can typically ignore those. And so that's what we do when we analyze this data. We take the Fourier transform to find out what are the characteristic tones, if you like, what are the characteristic frequencies which occur in these images. So this is how that looks like. Here is a simulated image, STM image, just like the one I showed on the previous slide. So there's one atom missing here, and then these ripples. And then we take the Fourier transformation, which is shown here. And now basically anything which is periodic in the image on the left is a point on the right. Okay, so this atomic square lattice here are these points here, because it's periodic here. And these ripples which you see here becomes the square ring here. And that's how we can analyze what the electrons do in the material. And so here this is done for some real data. This is how it looks like in the real space image. You can't really recognize all that much on that if you look at it. But if you take the Fourier transform, you can actually make out distinct patterns in that image, which we can then analyze to understand the behavior of the electrons in the material. And now what we do when we try to analyze that is we typically do our experiments where we get these patterns in what we call Fourier space, but then we try to come up with a model. We say we come up with a Hamiltonian. That's, if you like, the world formula for our materials, the analog. So we try to come up with a model which explains the behavior, and then we do a calculation to calculate how these patterns would look like based on the model, and compare that again with the experiment. And then typically iteratively improve our model until we think it gives a good description. And in an ideal world, if that's successful, we can then explain the properties of the material on a macroscopic scale. So the idea is you image the material on the atomic scale and understand what's happens there, and then try to understand from that how the material behaves itself. And if you understand that, you can also typically control it and tune it for specific properties. Oh, that's not working here. Okay, so here's an example of how that looks like in real data. So this is for Delafosite materials. They are called Delafosite after the person who's kind of found these, they are minerals originally, who's found these minerals and classified the crystal structure, a French person called Delafosse. And so this has the chemical formula palladium cobaltate, so there are layers of palladium here and then cobalt oxide. And what's peculiar about this material is that electrons can move very easily in the material, which is surprising given that it's an oxide. Normally you would say in a metal they can move easily. By an oxide you would say they cannot move so easily. And so we were trying to look at whether we can see in our microscope why they move so easily or how they move in the material. So we break these crystals, and then you would think, well, either you end up with these palladium atoms at the surface or with these cobalt oxide atoms, so it requires a bit of work to figure out what one sees. But this is the cobalt oxide surface of the material. You saw this image before with a hexagonal pattern, and this is the Fourier transformation, which shows a nice ring here from these electron ripples, and then these points from the crystal lattice here. And so here's a video of how this looks like now if we record one of these spectroscopic maps, where we can see these ripples as a function of the applied voltage, and you can see how they change their periodicity, how they change their wavelengths. And that's what we call the dispersion of the electrons. That's how we can image the electronic structure. And on the right is again this Fourier transformation I mentioned to you. And in the Fourier transformation, when these ripples appear, you can see a big ring appearing here, which kind of moves outwards as the energy goes down. And then we can take a cut through this data set and plot these, analyze them, and compare them to theory. So in this specific case, here's such a cut. You can see this dispersion relation here. Then we can compare that to theory. And in that specific case, one can then actually see that what we get from theory is actually reasonably well reproduced in the experiment. And in this specific case, we can then also understand that actually the spin of the electrons plays a role in how the electrons behave in the material. That was one of the things we could deduce here. Although I must admit, in this specific case, my colleague Phil King could have told me that beforehand, before we looked at it. But we were able to here basically confirm that using a different method. Okay, now let me show you an example. I told you initially that we want to control phases and control the electrons by some parameter. So let me now show you an example where we can actually control the electronic states in the material by some external parameter. Again, this builds on work which was done actually 15 years ago in St. Andrews by Professor Andy McKinsey at the time. So they just studied this material strontium ruthenate, which has this stoichiometry here, strontium ruthenate 327. And what they found is that if they apply a magnetic field to the material in a peculiar direction, then the current becomes different whether it flows in the same direction as the applied field or whether it flows in a normal direction with respect to the applied field, or better, the in-plane component of the applied field. So here, the red and the black curve here are the two currents in the two orthogonal directions, and you can see one of them is low, one of them is high. Which in principle is interesting because it means you can control current with a magnetic field, but it wasn't understood why that's happening. So we kind of thought, well, that's an ideal thing to study with our microscope, so we put one of these samples into our scanning tunneling microscope. So here's how it looks like. This is the crystal structure. We break the samples here in this place here between the strontium atoms. This is the strontium square lattice. You've already seen such an image, and two defects here. Now, if I have a material like this, it has a fourfold symmetry. I can rotate it and it looks 90 degrees and it looks the same. Then you would say that all the scattering patterns should have the same symmetry, right? So if I take a checkerboard and I put myself, for example, on this white field here, if I go, for example, to the left, right, or top or bottom, sorry, that was one too far, that should all be equivalent. It should be the same. Likewise, if I go in diagonal directions, It should all be the same. It should be fourfold symmetric. So let's look a bit closer at our sample. And then you see that these patterns actually are not fourfold symmetric. If I rotate this pattern here by 90 degrees, it looks different. It's not the same. This already kind of pointed to the direction that actually there is something happening, and maybe something similar is happening as what was seen in these transport experiments. So we decided to build an STM, or put it into an STM which has a vector magnet. Oh, this laser pointer is giving up. Sorry for that. I think I need to go to the computer. Okay, so we built an STM which has a vector magnet where we can apply the magnetic field in different directions. So we have two axes. Normally, if you buy a magnet, it has only one axis because it's like a tube, it's a toroid. And so you can only have the field in one direction. It's very complicated to build one which can apply a field in three directions. This one can do it in two directions, but we need three directions. So what we decided to do is we bought a magnet which can apply the field in two directions, and then we can actually rotate the microscope inside that magnet. And that allows us to then apply the field in any direction with respect to the tip sample geometry. So here's a movie where we rotate the magnetic field in the plane of the sample, and we want to look at how these scattering patterns look like. So here the magnetic field vector rotates, and you can see how the scattering pattern changes essentially following the magnetic field. Right? So here it points in this direction here, and then as the vector rotates around, it rotates in the 90-degree direction, and as it further rotates, it changes. So this, I should say, this is a very difficult to measure data set because you have over multiple days to rotate the insert without destroying the tip, and then you have to acquire these images. So it took a quite long time. So we were quite happy to actually get a full movie because you can't have any change in the tip or the sample over that time, otherwise you'll have lost the measurement. Okay, and now can one understand this? So we are very happy actually that we could model this behavior. I don't want to talk you through the details of it, but we can write such a world formula for the material where we can actually model that behavior of the electrons. And what's great about that is that basically means that we know what the important parameters are and how one might bring that from low temperature physics to actually, for example, room temperature or into different conditions. And so here, this is just to show you that we can actually calculate what's happening. So what we have to do is we have to model the direction of a magnetization of the sample, and which is here kind of shown by this compass rose. So if it points to the right, then the scattering pattern in the simulated image points to the right, just like in the experiment. And then if we flip that by 90 degrees in the other direction, the scattering pattern follows in the same follows directly that compass needle. And so we can model that behavior, which makes us confident that we actually understand the key physics of what is happening there. Okay, normally we try to also kind of make some semi-artistic renderings which represent our research. So this is the one which represents that work. So it's the compass rose which controls the electronic structure, and these ripples here are the ripples in the Fermi sea, which run only in one direction along the compass rose, but not in the other direction. Okay, so with that, I'm coming to the end of my lecture. So I've shown you a small part of the work which we've done in recent years. We've also worked on superconductors, and then recently there was one interesting example. We tried to, during the pandemic, we thought, well, maybe we should check whether our materials could kill SARS-CoV-2. So we had a project with the School of Biology and Catherine Adamson there, where basically we gave them samples and they put the virus on the samples and checked whether the virus survives, and we found some which actually killed the virus. Right, and let me finish with, so now I hope you can come up with something better. So I asked JetGPT to make an artistic rendering of representing our research, and I gave it for that basically the paragraph describing the research on our homepage. I thought that's a good basis. And well, this is what it came up with. Okay, and with that, I would like to thank you for your attention.
Good evening, everyone. It's a real pleasure for me to thank Professor Wahl for his entertaining and enlightening inaugural lecture. He really has showcased the tremendous contribution that he and the team he described have made to materials research, whilst also demonstrating, I think, how fascinating and engaging fundamental science can be. Probing the atomic nature of materials, searching for defects in single atoms, and visualizing the resultant ripples of impact that these defects cause. It's the kind of stuff that captures our imaginations, enthuses current scientists like myself, I think inspires future scientists, building the tools required to discover how electrons behave, working in an ultra-low vibration laboratory, which I have had the joy of visiting, and it is quite serene inside, discovering new properties that are fundamental to the nature of the things around us. I'm sure not only a geeky neuroscientist like me thought this was all pretty cool. And although research into the properties of materials at the atomic level is impressively complex, Peter did a fantastic job, I think, of highlighting the benefits and importance of this research. Apparently, the emails that some of us send in a day could power a car. This is really vividly highlights the need for people like Peter to lead the discovery of new materials that will provide solutions to major challenges, such as the sustainable use of energy. Whilst it might feel like we are reaching a plateau in terms of technological advances, the notion is dispelled by scientists like Peter, who are uncovering surprising and exciting new knowledge regarding the fundamental properties of materials, which will underpin step changes in technology that improve and protect our future lives. So I'm aware that I stand between you and our continued celebration, which includes a reception in Lower College Hall that I hope you'll all join us for. So I want to finish here with a quote from the New Zealand physicist. Some might pick the accent and know why I'm choosing a New Zealander, Ernest Rutherford. And I think this quote nicely highlights the benefits and importance of research, such as Peter's, that aims to understand the complexity of something so fundamental as the atoms we are made of. So Rutherford said, "All of physics is either impossible or trivial. It is impossible until you understand it, and then it becomes trivial." I'm sure you'll join me in thanking Peter again for a fantastic lecture, and also thanking him for being one of the scientists who strives to turn the impossible into the trivial.